Okay, continuing on with Calculus 1.3, lesson 1.3. Again, I keep showing you these pictures, but removable and non-removable, all right? Removable or point, okay, the two-sided limit exists. That limit from the left equals that limit from the right. But you wouldn't say this continuous because it has a hole in it, right? It has a hole right there. Limit exists from the left, limit exists from the right. So these are removable. The two-sided limit exists when you have removable and holes. When you have jump, the two-sided limits don't exist. So the minute you have jump, you don't have continuity, right? But just the one-sided limit exists and this sided limit exists. So the limit from the left exists and the limit from the right exists, but they're not the same. Same thing here. And by the way, for jump, one of these could be filled in and it's still not going to be continuous, right? One can be a filled in hole. Here's the same thing, only this time from the left it equals 2, from the right it equals 1. So if we were saying, again, it's not continuous because the left doesn't equal to the right, so the limit doesn't exist. And here's one where it's infinite. Okay, you have a vertical asymptote. So the limit from the left is negative infinity, the limit for the right is positive infinity. The limit doesn't exist, nor does the function at 0. Okay, here's a function that exists at 0, and the limit from the left exists, and the limit from the right is infinity. So the limits are not the same, so the limit doesn't exist at 0, but f of 0 exists. Okay. So let's see what all that means when we have to write stuff out. It says find the points or the intervals. So we're going to use interval notation at which the function is continuous. And so we're going to identify that first. And then the points at which the function is discontinuous and tell us what kind of discontinuity. Okay, so let's just write where it's the intervals where it's continuous. So I'm just going to use my pen. Oops. Coming up here. I'm starting, and it wants it from -5 to 10. So it's going from here to here, right? So I am continuous from -5, moving up, but then at -3, I have removable discontinuity. So -5 to -3, union. Then it goes from -3, keep going, because that's continuous, all the way till it looks like it has a vertical asymptote, right, at +3. So we would say -3 to 3. Okay. I'll do that a different color. So this one to 3. And then the next time it's from 3 to 5. So union 3 to 5. And then the next time it is from 5 to 7. And then it looks like the last time it is continuous from 7 to 10. So one more, union 7 to 10. Okay, so quite a bit of discontinuity going on there. So we have to talk about them each. Okay, so let's talk about the one at -3. It's discontinuous at -3. So you could say the discontinuities at x equals -3. All right, and it's removable. We have a discontinuity at x equals 3, and that would be infinite. This would be, I wouldn't even say that's a whole. Okay, sorry, just talking to myself. And then we have at x equals 7. Oh, x equals 5, sorry. Right here, That's removable. So this is non-removable. We're specifically calling infinite, but if they're just talking removable and non-removable. So this would be removable. It's got a hole. And then at x equals 7, we have a jump. And that would be non-removable too. So it's removable when all you have to do is fill in the hole. Okay? So otherwise, so jump and infinite are non-removable, and a hole or just a missing dot is removable. Okay? So let's go to the next thing. So this is important to know. There's something called one-sided continuity. And so things can be continuous from the left or continuous from the right instead of just continuous. So if you look at the definition, left continuous at x equals c is if the left side limit equals f of c. So like I'll draw a picture of that. So here's a function, and I'm going to put a hole right here. Or I'm going to fill it in though, and I'm going to call this c. So the limit from the left as I approach c is equal to f of c, right? So the limit as x approaches c of f of x is equal to c, and as you can see, it's also ending in the dot. So if it ends in the dot, basically if it ends in the dot coming from the left, it's left-sided continuous. And let's say f of c, and I put n equals, and which is equal to f of c. So you can see I was doing that. This should be f of c. Messing up here. The limit as x approaches c of f of x is the same as f of c. So, like I said, if you have a function and it ends with a dot, it's left-sided. Right-sided would be if it started with a dot. Right? So here's fill it in and like that. So I have, this is c right here, and I'm coming here, and the limit is equal to f of c, and f of c is filled in. So if the dot's on the right hand. So let's go back and look at those graphs we had here, and I'll show you. So like this has right side continuity because this is filled in and it's coming from the right. It does not have left-sided. This has neither left nor right, neither left nor right. This has right-sided. This has left. See how it comes up here? Has left-sided. So I hope that makes sense. Okay? Oops, there was more stuff on here. Okay. Continuity at a point just means the limit is equal to that. So continuity point is what we were talking about. It just means that it's continuous at that point. So you have one-sided continuity at a point, but then you got continuity at an open interval. And all that means is if you have this picture, I come from here and I go to there. So I have an interval from A to B. And that's my function. This is my function, f of x. That is continuous on the open interval from A to B. There's a hole on either side. Doesn't include the endpoints. So you can say it's continuous. I'm going to do in the green. This part is continuous. So it's continuous on the open interval. Open interval would be soft brackets. Now continuous on a closed interval would be if you had the same function and you had dots on either end. So that means you use hard brackets for a closed interval. And so you say, okay, how do I know if it's continuous on the closed interval? If this part is there and there's no holes in that part from A to B, and then you have include A and include a dot B. So those are more vocabulary words. One-sided continuity, continuity at a point, continuity on an open interval, and continuity on a closed interval. All right, more to come.